Welcome to this lesson 5 in this course of manufacturing for turbines. In today's lecture, we will see manufacturing processes and manufacturability. So continuing from the previous lesson, we will complete the discussion on engineering materials in which we will cover the details about ceramics and composites. After that, we will move on to manufacturing process and manufacturability of materials where we will look at materials information, manufacturability and basic properties of materials which influence the manufacturability. So we have already understood this classification of engineering materials in terms of metals, plastics, ceramics and composites. In today's lecture, we will see details about ceramics. So in ceramics, we know these are compounds of metal and non-metallic elements. Ceramic is basically a term derived from kermos, which means potter's clay. So use of ceramics is very old. It can be traced back to up to 4000 BC, where ceramics were used to make pottery and bricks. Ceramics are widely categorized into categories. First category are the traditional ceramics. So traditional ceramics, these include whitewares, tiles, brick and pottery. Industrial ceramics, this include cutting tools, semiconductors, gas turbine components, automotive components which is, for example, include spark plug. Examples of engineering ceramics include simple oxides like silicon oxide, aluminum oxide, iron oxide, etc. Mixed metal oxides, they are also come in the category of ceramics. And then we have nitrides which are used in several hard coatings. Examples of nitrides which are used in hard coatings include silicon nitride, aluminum nitride, etc. Now the distinguishing features of ceramics. So ceramics essentially consist of a compound or a mixture of metal and non-metallic elements. So this means always in ceramic one of the atom will be a metallic element, other element will be a non-metallic element. So ceramics are also characterized by low density than most metals, because here generally the combining non-metal is either oxide or nitride or maybe carbide. So because of that the density is much lower compared to traditional metals. Ceramics are also generally strong than metals, especially in compressive loading conditions. They have low resistance to fracture. This means they have very low toughness. They cannot absorb much energy, and often it is known that ceramics they fracture under impact loads. They have low ductility and low malleability, means they have low plasticity. They have high melting point. They are poor conductors of electricity and heat. They are single crystals when they are transparent, and except for glasses, most of the ceramics they exhibit regular arrangement of atoms. They are resistant to heat and they are chemically stable. Applications of ceramics, they include several electrical insulators, abrasives, cutting tools, thermal insulation coatings. This is particularly useful when we will look in the gas turbine manufacturing. So the thermal barrier coating in the gas turbine blades, it is used there, utilizes ceramics. Then windows, screens, etc. in form of concrete, also it is used in highways and roads. Biocompatible coatings are used in scaffolds, etc. Magnetic tapes, body armor, hip implant, and radiation shielding. So these are the some of the representative applications of ceramics. So in the subcategory of ceramics, we have glasses also. So glasses are amorphous solids with the structure of liquid. So these glasses are produced by supercooling at a very high rate so that the crystals are allowed to form. So glasses, they generally don't have a distinct melting or a freezing point, and their behavior is very similar to ceramics. So glasses are widely used in window glasses, container glasses, or they are also used to make fiber glasses which are used as a reinforcement in several composites. These are some of the examples of glasses which include soda lime glass, lead alkali glass, borosilicate glass, fused silica glass. Next, we look at details about composites. Now, composites are basically a combination of two or more chemically distinct and insoluble phases. So, these are hybrid class of materials where the properties of the composites are superior compared to its constituents. Another distinguishing feature of composites is basically the constituents in the composites. They are distinguishable and they do not combine on a microscopic level. Rather, the constituents they combine on a macroscopic level. So this means that we can distinguish the both the constituents there. And generally, in case of composites, we have the reinforcement of different types, which can include fiber or filament or particulate, etc., which are characterized by high strength, high stiffness, and low density. So, because of these properties, the filament and or the particulate, they come in the category of reinforcing phase, which is surrounded by the matrix. Now, this matrix can be either a polymer matrix, or it can be a metal matrix, or it can be a ceramic matrix. So, matrix generally is covering the reinforcement from all the sides, and it exhibits good shear properties, low density, and combining the reinforcement and matrix, it gives a result of a composite which is generally having high strength, high stiffness, good shear properties, and low density. And here the essence of combining the both the things, that is the matrix and reinforcement, is because we have a physical distinct interface between the, say, fiber or the reinforcement and the matrix. So we can distinguish both of them, and there is no reaction or no combination on the microscopic level. Now, if we talk about composites, so composites, they utilize fibers, especially the structural composites, which are, say, used in aerostructures or maybe the wind turbine blades. So they utilize fibers, especially the synthetic fibers like glass fiber, carbon fiber, or in some applications Kevlar or boron fiber may also be used. And in many applications, natural fibers which are derived from plant and animals may also be used as reinforcement. In terms of matrix, so the matrix material can vary between polymer, metal, or ceramic. In case of polymers, thermosets can also be used, and thermoplastics can also be used as the reinforcement. So we know from our previous lesson that thermosets are basically polymers in which permanent cross-link bonds are developed, and then what happens once the permanent cross-link bonds are developed? So here the remolding upon application of heat is not possible. In case of thermoplastics, we know there is no permanent crosslinks, so because of which we can remold them upon application of heat again and again. And in metals, many a times it is observed the non-ferrous metals are used as reinforcement to develop metal matrix composites, which include aluminium, magnesium, and titanium. Then we can also have ceramic based composites where silicon carbide or silicon nitride or aluminium oxide based matrix materials are used. So as I have already mentioned that ceramics are very popular in applications which have high strength and less weight. So aerospace application is one of the largest users of composite materials here. Now with that we enter the next module of this next discussion topic of this course, which is the manufacturing processes. We will be spending some time in discussing the overview of the manufacturing processes. Nevertheless, we are not going to go in specific details. So manufacturing processes, as we know, are basically processes to convert raw material. So we convert this raw material into finished goods. And then what happens in this, once we are converting the raw material into finished goods, so there can be either primary shaping processes, or there can be secondary shaping processes, or there can be joining processes, or there can be surface treatment processes. So some of the processes in case of primary shaping, they include casting based processes, in which we have sand casting, die casting, investment casting. Then we, in the case of molding methods, which are specially popular with polymers, we have injection molding, compression molding or blow molding. Deformation based methods like rolling, forging, drawing. Powder metallurgy based powder based methods like sintering, hot isostatic pressing, slip casting is there. Composite forming methods are there like hand layup, filament winding, resin transfer molding. Then we can have special methods like rapid prototyping, layup, electroforming, etc. In case of secondary processing, we have machining or heat treatment. In machining, we can have wide variety of processes like cutting, drilling, etc. Heat treatment can be there where we have quenching, tempering, edge hardening, etc. Joining processes are there which include fastening using rivets, or we can have welding which is fusion based or maybe solid state. We can have heat bonding, we can have snap fits, we can have adhesives, etc. So surface treatment methods can also be there, which include to engineer the surface of the developed product. This include polishing, texturing, plating, metallizing, anodizing, painting, etc. And by completing of all these processes, basically we convert this raw material into the finished product. So for any product, it is not just one manufacturing process which is used, rather the sequence of manufacturing processes are used, and this is dependent on the material which is used in making that particular product. So we will just now see overview of all the manufacturing processes as shown here, starting with this casting process. So casting process is one of the primary shaping process where we have a mold which is created using a pattern. So in the mold is basically a cavity which takes the shape of the pattern, and upon pouring molten metal into this mold cavity, upon solidification, the molten material, it takes the shape of that mold cavity. Now this depending on different types of molds, different type of pattern, there can be different type of casting processes. So popularly we have sand casting process where we have the mold made up of sand. Then we have die casting process where we have permanent mold made up of metallic molds, and this is popular with non-ferrous based materials. And upon solidification here, what is done, the mold is not broken, rather with the help of these ejector pins we can remove the solidified cast product. Then we have investment casting process where the casting is done using wax patterns. So this is very popular, especially with making the gas turbine blades. We will see in much detail as we go forward in this course. And then there is low pressure casting where we have zirconia sand mixed with binder, and with the help of low pressure maintained here, we can pump into the liquid or molten metal. And sometimes we also utilize cores in order to create some cavities or hollow castings as per the requirement of the end product. So then next are the forming based processes. So forming based processes are just the processes which change the shape of the product by applying stresses beyond the yield stress but less than the fracture stress. So it is that the forming processes, they function in the plastic zone of the loading deformation of the particular material. So in this case we have forging process where we have two dies in which the workpiece is placed, and upon applying these compressive forces the workpiece takes the shape of these dies. Then we have rolling process where in case of rolling we have these two rolls through which the workpiece is passed and it takes the shape of this cross section between the rolls. Or we can have extrusion where we have a billet, it is pushed through the die, and while it is pushed, or the product takes the shape of the die opening. Or we can have this type of a spinning process where sheet metal can be shaped into appropriate shapes. Next are the machining processes as discussed earlier. So machining is basically a secondary processing of products where of course we want to have different shapes imparted, or we can have different forms imparted to the product, especially if we want to have a smooth surface or we want to create some hole, etc. So in machining processes what happens, there is a relative motion generally known by relative motion between the cutting tool and the workpiece. So in conventional machining, there is a relative motion between the cutting tool and workpiece, and this relative motion between the cutting tool and workpiece is achieved using a machine tool on which the workpiece and the cutting tool are mounted. So now this relative motion creates this applies these forces, and stresses are induced, and essentially the shear stresses are induced, which cause the formation of chip in conventional machining. And in conventional machining, as shown here by example of turning and milling, the performance of the conventional machining is much dependent on the hardness of the cutting tool. So this green color is, for example, the milling cutter or the single point cutting tool used in turning. So generally in conventional machining, the hardness of the cutting tool is much higher than the hardness of the workpiece. So machining is not only done using conventional methods, but there are several non-conventional methods where energy in some other form, maybe heat, chemical, plasma discharge, etc., or maybe the kinetic energy of abrasives can also be used to remove material. So like for example here it is shown the plasma cutting process, where this plasma beam is generated, and then this plasma beam, as we know, is having very high temperature. So this is a thermal based machining process. So this plasma beam interacts with the base material, and because of which wherever it is interacting, the melting of the workpiece takes place, and consequently material removal takes place. Then we have electro discharge machining, where several electric discharges between the tool and workpiece, they remove material. And we can also have water jet cutting, where we have abrasives entrained in high pressure water stream, and when this high pressure water stream strikes the surface of the workpiece, so because of the inherent hardness of the abrasives, we can remove material and machining can take place. So we can say machining in all senses, be it conventional or non-conventional, is a subtractive manufacturing process. So it means material is getting removed in machining process. Next we have joining processes. So joining processes are also secondary processes, where we join two different parts which are produced using previous processes as discussed. So they can be cast, or they can be formed or machined. So joining is very essential. So we can have different methods of joining depending on different types of materials. So very popular adhesives are used in many joining processes, which basically is a form of a glue which are applied on the faying surfaces of the products which need to be joined, and then subsequently some pressure may be applied to help the adhesive to join the two parts. Sometimes these adhesives may also need some heat, as they need also curing. So sometimes heat may be applied, or leaving that adhesive in the atmospheric condition may also result in the joint. So now we can also have the joining using various fasteners. So this joining using various fasteners can be done using several fasteners like rivets, screws, or maybe snap fits. So what happens here, the screws, etc., or rivets, we can drill holes, and subsequently these can be applied. So this can be temporary fastening, where we can open up the joint as per the need, especially when we want to do some repair or maintenance. But the previous case, adhesive joining, is a permanent joining. So below we have the example of fusion welding, where example of manual metal arc welding is shown, where we have an electrode and a workpiece, and an arc is created between this electrode and workpiece, and because of this arc, melting takes place and complete fusion of the base material, and the filler may also take place. We also have example of welding from hot bar polymer welding process, where heat from this hot bar is used to melt the polymer sheets and join them. This is more popular with polymer based materials, and this arc welding is more popular with metal based materials. Fasteners, they are very versatile, they can be used with polymers or metals as per the need. So after understanding all these basics of the manufacturing processes, it is important to understand how the different material properties, they influence the manufacturability of any product. So any material, it has a different set of properties, and then this different set of properties can be useful, very useful in, say, gathering some test data, and based on the test data we can determine what is the allowable range of all these properties, and based on this range we can set specific design guidelines, where we can develop the guidelines to map the material to potential applications, and in the end we can do a economic or a business case study that by utilizing that particular material for a particular product, whether or not it is profitable to manufacture such using such materials or not. So we start with the raw data, which is generally obtained from lab-based tests on developing materials. So using several standards to determine these test data, we can develop samples and gather a lot of test data on a lab scale. And generally, this test data is collected for a wide range of materials, a wide range of samples, so that we know the variability of the data. So it is not always a particular value which is available, but it is the values are available over a range. And what happens when we have these values over a range, we can understand what is the variability in these properties. Because this variability is very important for the design process of any product. And because in the design we look at what are the allowable stresses which a particular material can take, and what are the failure criteria which can be applied in a particular scenario. So if you look at the manufacturability of the materials, so here what happens, the manufacturability of the materials is dependent on the basic properties of the material. These also are dependent on the performance, processing and structure of the material. So this interconnection between all these four parameters influence the proper performance and manufacturability of any material for a given product. So basic properties which influence manufacturability for any material include strength, that is how much load the particular material can take. It also is dependent on the hardness, which is resistance to scratching. It is dependent on the toughness, how much energy can be absorbed, what is the melting point of the material, that is the temperature at which the material changes phase from solid to liquid, what is the viscosity, that is tendency to flow in molten state, what is the tendency to form oxides, which is captured using the tendency of oxidation. So using these different properties, we have specific maps developed where different properties of the materials are mapped together. So here, for example, it is shown the density of the material on the x-axis and the strength of the material on the y-axis. Then all the materials that we have discussed up to now, which include plastics or polymers, metals, ceramics, composites, other natural materials and foams. So for example, here if we look at this chart between the strength and density, so here density of the material, so here we can see the foams, they have much less density and their strength is also much less. Here importantly, it is important to note that the scale of these graphs is not the linear scale, rather it is a log scale. So the properties, they increase tenfold at the next major point. So what happens here, that the foam, for example, in case of foams, the density is much less, but if you then compare with the metals, so the density is much higher. So now what happens here, that using these maps we can pick the appropriate material and use it in the specific application. So in this slide we look at the representative maximum service temperature for various materials. So we have seen that how strength and melting point or maybe the hardness etc. they influence. So it is very important to understand this concept of service temperature also. So service temperature is basically the temperature at which the product will satisfactorily perform its intended function. So based on the classification of materials that we have understood, that is metals, polymers, ceramics and hybrids, we can see that certain materials, they are having service temperature very less, maybe up to 500 degrees C. Most of these carbon steels, copper based alloys, aluminum based alloys or magnesium, they function below 500 degrees centigrade. And whenever there is requirement of high temperature materials, so of course we have refractory materials like tungsten based alloys, or we can have nickel based super alloys, which are widely used in gas turbine blades, as we will see in the next few lectures. Then in case of polymers, so we know polymers, they cannot sustain very high heat, so their service temperature is generally of the order of 100 to 120 degrees centigrade, and for some polymers it may be even less, near the room temperature and so on. For ceramics, we know they are very stable at high temperature. So what you will observe here that most of these ceramics, they have very high service temperatures of the order of more than 1500 degree centigrade. So service temperature is also important to understand from the melting point perspective. So generally the service temperature of any material, this may be around zero point 0.4 to zero point 0.6 of the melting point of that particular material. So all these ceramics, they are having very high service temperature. So all the high temperature needs are fulfilled using the ceramics. And in case of hybrids which include composites, we have the ceramic foams which have particularly very high temperature. But all other engineering structural polymer composites like CFRP, JFRP, they have service temperature of the order of 120 to 100 degree centigrade. Then we can also look at the representative comparison between the strength and the toughness. So strength is the maximum load carrying capability and toughness is the total energy absorption of the materials before failure. So here it is observed that metals, they are generally having high toughness and high strength, and at the same time ceramics or glasses, whatever we have discussed, they have low because of low toughness, so they are on the relatively right hand side of this left hand side of this curve. Then relative hardness and approximate strength. So for most of the engineering materials, hardness and strength, they are directly proportional. And hardness, we know, is the ability to resist scratching. And hardness can be measured using various hardness scales like Rockwell, Vickers, Mohs, etc. And wherever the materials are known to have high strength, they are also known to have high hardness, in fact. Then very important, price of the materials. What is the price per unit volume? Of course, this is very important once we are making products, because the cost of the product also carries the cost of the raw materials that go into making it. So some of the metals like the cast iron or aluminium based metals or carbon steels, they are of relatively less cost as compared to other metals and alloys like nickel based super alloys, titanium based materials are there. Polymers, so most of the polymers, they are having less cost, even lesser than the metals, but some of the polymers like PEEK or the PTFE, they will have significantly high, relatively higher cost compared to the other counterparts in the polymers. Ceramics, so traditional ceramics which we have discussed like stone, brick, etc., glass are of low cost, but engineering ceramics like aluminum nitride, tungsten carbide, boron carbide, all these they have very high cost. And of course in case of composites or hybrids, so like glass fiber, carbon fiber especially is having very high cost because of the high cost of the reinforcement here, and all other hybrid materials are placed as per the relative cost. So it is very important to appropriately pick the material as per the cost, because cost of the product is largely dependent on the cost of the raw material. So with this, we summarize the lecture for today. So what we have understood the details about the engineering materials. In engineering materials, what is done, that we have looked at ceramics and composites. Then we have looked basic classification of manufacturing processes. We have looked at the manufacturability. So what properties they influence the manufacturability of any material. Then we have looked at certain property maps. We have looked at, for example, comparison between strength and density, comparison between toughness and strength. Then we have looked at the concept of service temperature. We have also looked at concept of relative cost and how they influence the selection of the appropriate material. So with this we complete this lesson, and in the next lesson or lecture we will look at the mapping between materials and their manufacturing processes in terms of mass component, tolerance, section thickness, surface roughness, economic batch size, shape of the component, and then we will summarize the manufacturing processes, how we have to select the appropriate manufacturing process. Thank you.